All right, we'll get started anyway, guys. So, two things I've handed out to you. The first is the skills checklist. Okay, so we'll have a read through of that. It's an opportunity for you to tick off skills rather than exercises, because this is what is going to be in the test. This is the content of the test. And the point of this is to say if there's a particular skill to localize, that is to find out what are the areas I need to work on. And then I can direct you to where in the textbook that is, or I can even make some extra questions around certain skills that you might find challenging. Okay, so that's the first thing that we've got there, where it says chapter 12 and chapter 13. Following that, we have the review set questions. So the review set's in the back of the textbook, so the back of the chapters, so chapter 12 and 13. Most of the questions are relevant, but not all of them. So you'll notice there's some that are missing, but they're the ones that are relevant to the test and to the unit that we're doing. Okay, turn over the page. What we have here is a comprehensive review. So it's double-sided, and this is what we are going to work through together in a moment. So we're going to go through all of this, opportunity to emphasize all of the skills. We'll go over it reasonably quickly, but I'm happy to pause and answer questions along the way. That's a good summary of everything in the unit. I've also handed out to you a practice test, okay? So this is the formative test that I'm handing out to you. It's up to you when you do it. It's up to you how you use it. If you want to do it as a closed book sort of standard 80-minute test like you would in the lesson, you can do that in your own time, or you can come in and do it during the lesson. I'm not going to dedicate test time to have a formative test. It's up to you how you use the resource. Now, solutions to this will be emailed to you tonight, along with a number of other extra revision resources. So I'll have an email coming out to you with a summary of revision resources, and what we're going to do today is work through the checklist. Are there any questions so far? Okay, so the test is Thursday next week. We will have graphics calculator that's permitted and a single side of A4 page of handwritten notes. So let's rip straight into these then. You might be able to squeeze it onto the sheet, but I squeezed all the questions on there. So I would anticipate you probably want to do this either in your book or on some extra paper alongside. But we're going to go through these problems together. So we started with Surds, right? And we've got evaluate and simplify the following Surds. So I've got 2 root 3 plus 5 root 3. This is just like with algebra. We've got 2 lots of root 3 plus 5 lots of root 3. We add them together, that's going to be 7 lots of root 3. On to B. We've got root 3 multiplied by 2 plus root 5, take root 3. Okay, so the root 3 is going to distribute to every term in the brackets here, right? So it's going to be 2 lots of root 3 for the first one. It's going to be root 3 times root 5 for the second one. And for the last one, root 3 times root 3 simplifies to 3. Now the root 3 times root 5, we can express that as the root of 3 times 5, which we know is 15. So we could put that in as root 15, and then we have to take away 3 sitting there. So A, B, C. Now with C, we have the square root of 75, and one of the ways we were taught to simplify Surds, so Sam, we'll work through this together, mate. I reckon copy this down, and anyone else who's not. So Alfredo, Francesco, we're going to go through this worksheet together.
Yeah, I'm doing.
Excellent, good stuff. Yep. I don't know, that looks like the test, mate. This one.
No, we're doing this one.
Oh, yeah, good. You've got the test sheet open. Yep, excellent. Yeah, good. All right, so where have we got square root 75? All right, we need to say how can I express this number with the product of a square number? So the square numbers are 1, 4, 9, 16, 25. Okay, root 75, that's equal to 25 times 3. Okay, this is the largest square number, that's a product of it. And then we can express that as the square root of 25 times the square root of 3. And the square root of 25 is 5, right? 5 root 3. Okay, so that's question 1. Any questions so far? Okay, on to question 2. In order to rationalize the denominator, we multiply by the conjugate, right? In this circumstance, we've got root 3 at the bottom, so we're going to multiply it by root 3 on top of root 3. Okay? And so then we know at the bottom, root 3 times root 3, we're going to have 3 as the denominator. And at the top, we'll just have 2 lots of root 3. Okay, so the different ways, rationalize the denominator means make the denominator a rational number. Okay, over here the denominator is irrational, right? Square root of 3. And so we have these 2 ways. I'm just going to write out, this is what the question was, and this is what we've made it equal to. You can see the denominator is a whole number. It's rational, it's an integer. Okay, on to question 3. We're talking about index laws. So we start here, we've got p to the 5 on q squared on top of p to the 7. Okay, so we can only collect them using index laws if they have the same base, right? So here we have p to the 5 and p to the 7 at the bottom. And if you can see the answer, you can go straight to it. But I'm going to write it like this. It's the top power, take away the bottom power, right? We don't have anything at the bottom once we take it to the top. So get rid of that line there. Now 5 take 7 is minus 2. So we have p to the minus 2, q squared. And when we have a negative power, that can take it to the bottom of the fraction to make it a positive power. So this one simplifies to this here. All right. Now, we'll be very precise about how we want you to express it. If there's ambiguity, then you can express it here or here. The idea is you just have to simplify it. And the simplification is the breaking down of the powers. Okay? So if it says express with negative indices or without fractions, that means you express it at the top. If it says express without negative indices, that means we'd express it that way because both powers are positive. Okay, let's move on. We've got b, which is 3x in brackets squared. Now, because of the brackets, the squared needs to apply to both of these inside the brackets. So that's 3 squared x squared, which is 9x squared. All right. Now, my point with c was to only show you if we have 1 on x to the 5, not that this is a simplification, but if it says express without a fraction, express it at the top of the fraction, x to the minus 5, all right? So that's for C. Okay, for D, we have root x on top of x squared. Now, this is the rational indices. So when we have like square root, we know that that is x to the power of a half. And at the bottom we have x to the power of a 2. So now they have the same base. All right, then we're going to do the top power, take the bottom power. And this will be to the negative 3 on 2. Okay, so we'll give you full marks there, unless it says write without negative indices, in which case we would express it like that. Any questions so far? Okay, on to E. I'm going to be clearing them off as I go to make room. So if we've got E, we have 4 to the x on top of 2 to the 1 take x. So if we can simplify this using index laws, we need to have the same base. And I'm looking at that, I'm going, I know that's a power of 2, and so is that. So I'm going to make that 2 to the 2, even then, let's not even worry about the brackets. It's 2 to the 2x. All right, 2 to the 2 is 4, which would make it 4 to the x at the top, and 2 to the 1 take x at the bottom. And then when we collect these, it's the top power take away the bottom power, right? 2 to the 2x take away 1 take x. Now, one thing you have to watch out for with this kind of question is when we subtract the bottom power has a negative in it. So that means I've had to put it in brackets so that that negative distributes. It applies to both terms in the bracket. So it's 2x take 1 plus x. There's a negative. We've got take away a negative, it makes it a positive. So 2 to the 3x, take 1. Okay? And on to f. We've got minus 2a squared on top of b, all to the power of 3. So everything in here is going to the power of 3. Now, with this negative out the front, all we're going to do is we're going to say, if we have a negative to an even power, it gets rid of it, doesn't it? It's to the power of 2, to the power of 4, to the power of 6, because a negative times a negative makes it positive. But if we have a negative to an odd power, the result is going to be negative, okay? So that means our answer is going to be negative, and then I'm just going to apply the 3 to everything in here. So we're going to have 2 to the power of 3, a to the power of 2 times 3, and b to the power of 3. So that's negative 8, a to the 6 on b cubed. So that's our index laws one. Am I going too fast, or everyone okay? If I go too fast, let me know. All right, so question 4, we've got write the following numbers in their opposite form. So this one is expressed in scientific notation, and we're going to express it in the opposite form, which is represented as a decimal. So when we have to the power of negative 5, what we do is we write 5 zeros, or 1, 2, 3, 4, 5. We put the decimal after the first 0, and then we list the digits that we're given here, 3, 4, 1. Now your calculator can do it for numbers that have sort of low powers, but when they get a bit higher, the calculator gets a bit confused. Okay, then we've got 7,680,000. So this is expressed in decimal form. We're gonna write it in scientific notation. So it's going to be 7.68 times 10 to the power of something. And the question is, how many places does the decimal place have to move? So if we're putting the decimal place here, we can see there are 6 numbers to the right of the decimal place. So 1, 2, 3, 4, 5, 6, 7.68 times 10 to the power of 6. All right, very good. Solve the following by equating the bases. So that's A, that's B. So if we're equating the bases, what we need to do is we need to make both sides of the equation have the same base. So here I've got a base of 3. I need to express 27 with a base of 3. 27 is 3 to the power of 3. And so the solution is, because the bases are the same, the powers have to equal. The solution is x equals 3. Alright, when we get to a question like B, before we can make the bases the same, we need to get rid of this product out the front. So I'm going to divide both sides by 5 to begin with. So we're going to have 2 to the x take 1 equals 4. Then I'll make the bases the same. 4 we can express as 2 squared. The bases are the same, so now we're ready to equate the powers. Okay, let's go on to logarithms then. And so we're just simplifying logarithms. We start in base 10 and then we move on to a few different bases. So this is question 6. We have log of 100. And so when we have log just written by itself, that means log in base 10, right? And so we need to express this number as a power of 10. Log of 100 is log of 10 squared. And once we have expressed it as a power of 10, it simplifies to the power. Okay, log of 10 on the square root of 1,000. So you can see why we do the index laws, right? Because all in here, we have to use index laws to express this as a single power of 10. So at the top, I've got 10 to the power of 1. At the bottom, I've got 1,000 to the power of a half. That's what the square root means, right? That's to the power of a half. But I also know 1,000, that is 10 to the power of 3. Alright, so there's a couple of things going on there. I've got the half is the square root, and 1,000 we write as 10 to the power of 3. And then I'm going to use the index law here by multiplying those powers together. Alright, and now they have the same base at the top and the bottom, so now it's going to be the top power take the bottom power. So 10 to the 1 take 3 on 2. So 1 take 3 on 2. Now these kind of things, like I think I've explained enough. Important to know how to do them manually. But if we have 1 take 1 and a half, we're going to have minus half. And so we've expressed all of this, we've simplified that to a single power of 10. The answer is minus half. Alright, so a fair bit involved in that one. Any questions? Okay. Here we have log in base 2 of 8. So when there's a subscript there, that means we have to express this number as a power of that subscript. So here we have 2. We have to express 8 as a power of 2. We have 2 to the power of 3. We've expressed it as a single power of 2. And so now it's going to evaluate to the power. Alright, we have ln e to the 5 on top of e to the x. So this is the logarithm in base e, right? So we need to collect those first using index laws. The top power take the bottom power. We've expressed it as a single power of e, so it will evaluate to 5 take x. I might just make a connection here while we're here. Like with this one, we have ln e to the 5 on ln e to the x. Remember, one of the log laws is if we have ln a take ln b, we can write that as ln of a on b. Okay? Now that means we can go back the other way as well. If these are equal, it's an identity that holds. And so if we have ln e to the 5 on e to the x, okay, we've got ln of a on b, we can split it like this, and we can make it ln e to the 5, take ln e to the x. And we know from the laws of logarithms, ln e to the 5 simplifies to 5, ln e to the x simplifies to x, and so we've got the same answer. Okay, so all I'm doing, pointing out connections using the laws of logarithms. Okay, let's move on to question 7. We've got simplify the following logarithms. We have log of 20 plus log of 5. Okay, so the rule is, if we're multiplying them, log A plus log B, if we're adding them, it becomes log of the product of A and B, doesn't it? Okay, so here we're going to have log of 5 times 20. which is log of 100. Okay. Now, I'd probably give you full marks there just because all you're asked to do here is simplify it. But technically, log of 100 is log of 10 squared, which is 2. So if it can be simplified to an integer, you probably should do it, all right? Yeah, a lot of them you can't, but every now and then you have. If this can be expressed as a base of 10, which it is, 10 squared, we can simplify it. All right, and on to B, we have 4 lots of ln 2, take ln 8. So before we can collect them to be a single logarithm, we need to move this power up the top. Okay, remember that's one of the rules that we've been doing. We've been bringing it out the front when we use it for solving equations. Now we're doing the opposite. We're taking it up here. 2 to the 4. Now 2 to the power of 4 is 16. And then we have ln A take ln B. It's ln of A on B, which simplifies to ln of 2. Flying through it, it's good. Short units, one. Okay, so on to question 8. Write as a logarithmic or exponential statement. So here with the first one, this is an exponential statement. 3 to the power of 4 equals 81. If we're going to write this as a logarithmic statement, we're going to say the log in base 3 of 81 is 4. Okay, so we've gone from an exponential statement to a logarithmic statement. So that's the base, okay? That's what it evaluates to, and that's what we're performing the logarithm in base 3 of. That's A. B, same thing, this is an exponential statement. 10 to the power of 4 is 10,000. So what this means is log of 10,000 equals 4. I don't need to put the subscript here 10 because, I mean you can, like you won't get penalised if you do, but log just by itself means log of base 10. Okay, so they're the logarithmic statements. Now we've got, we're moving from a logarithmic statement to an exponential statement. Okay, I have log in base 5 of 25 is 2. All right. So think about, here we moved from an exponential statement to a logarithmic statement. Here we're doing the opposite, okay? So that is the base. So my base here is going to be 5. 3 to the power of 4, okay? So I'm going to have 5 to the power of 2, and that's equal to 25. Obvious statement, right? 5 squared is 25. And then, again, log in base 6 of 36 is equal to 2. 6 squared is 36. Okay, this is the skill we did yesterday. All right, solve the following logarithmic equations. 4 to the x is 20, and 2 times 3 to the x take 1 equals 17. Okay, so when we're solving an exponential equation using logarithms, what we have to do is log both sides, right? So we can log, we can ln, doesn't matter. I just use ln because that's what we tend to do in year 12. Okay, we'll put the natural logarithm on both sides. We're going to pull the x out the front, so we'll have x ln 4 equals ln 20, and then divide both sides by ln 4. Now just to emphasize, ln 20 on ln 4 is not equal to ln of 24. Okay, those are not the same thing. This is ln is an operation that you're performing to that number. Okay, so that takes precedence over the division. All right, so keep that in mind. X equals ln 20 on ln 4. So that's the solution for the first one. That's what we call an exact answer. Okay. Now, when we get you to solve equations using logarithms, more often than not we will say find the answer exactly. because we're interested in the process of performing the logarithms rather than this answer, okay? If it wants it to 3 significant figures, then that's when you would calculate it. If you're performing a population, all right, ln 20 on ln 4, that doesn't make any sense in terms of the population, so you would evaluate that to 3 significant figures. Okay, on to B. 2 times 3 to the x take 1 is 17. Our first step, we've got to get rid of this product out the front. 2, we're going to divide both sides by 2. So we'll have 3 to the x take 1 equals 17 divided by 2 is 8.5. Then we'll log both sides. All right, I've said it doesn't matter if you use ln or log, or even log in base 2. Let's just do log in base 10 of both sides. Okay, we'll move the x take 1 out the front. And put it in brackets. We'll divide both sides by log 3. And then we'll plus 1 to both sides to get the x by itself. Okay, so here we're going to expand this. Now, you can use FOIL. You could use FOIL here, but this is a difference of 2 squares. It's of the form a plus b times a take b. So you've got to keep your eye out for those because they pop up a fair bit, and that simplifies to a squared take b squared. So when we have 3x plus 2 times 3 to the x take 2, it's going to be 3 to the x squared take 2 squared. A squared take b squared. Alright, and multiple ways of writing this. This is 3 to the 2x take 4. You could even write it as 9 to the x take 4. Okay, so when we first got exposed to this, we did expansion, and then we started with something like this and factorized it back to that. Okay. What else to say about that? Something else that popped up. Oh yeah, so you can use FOIL. You don't have to use the difference of 2 squares rule. It's just that it's faster. So if you use FOIL, you'll find the middle term cancels. All right, on to B then. And this one we're going to factorise. So we expanded the first one, let's factorise the second one. 5 to the x plus 2 plus 5 to the x. So if we're going to factorise, what that means is we want a factor that's common to both terms. So this one here, we can express this as 5 to the x times 5 to the 2, can't we? That's what's happened here is the powers have been collected. That means they have the same base. We can go back the opposite way. If we have this expression, we would add the powers together. That's what we would obtain. So we can go back the opposite way, right? So this is what we would have. And now, what's common to both terms? 5 to the x. I'm going to pull that out the front. So we're left with 5 to the x times 5 squared, which is 25 plus 1, and 25 plus 1 is 26. Alright, so when we factorise it and simplify it, that's what it becomes. Okay, one more question. We've got 11. Question 11. A paddock initially has 2 rabbits. The population of rabbits grows at a rate of 16% per month. So remember, for population growth, P0 times 1 plus or minus r to the power of t. So our initial population is 2, and we're growing at a rate of 16%. So that's going to be plus 0.16, and that's to the power of t, where t is the time in months. Determine the equation of growth. That's part A, that's done. This is the equation of growth. The population of rabbits follows this equation. Part B, determine the population after 5 months. So that means when time is 5, how many rabbits are there? Well, that's going to be 2 times 1.16 to the power of 5, and we'll evaluate that in our calculator. 4.2 rabbits after 5 months. Round to the nearest number. Makes sense in the context of the problem. Okay, how long, using logarithms, determine how long it takes the population to reach 100 rabbits. So that's when the population equals 100. That's when P of t equals 100. How long does it take for there to be 100 rabbits? So this is an exponential equation that we're going to solve. Now, when we did it in chapter 12, we did growth and decay in chapter 12, we looked at how to solve this using our calculator, right? We looked at graphing that equation and then G solving the X value when the population was 100. So you need to know both, and they both support one another as well. Like, let's do it using logarithms and then we can check on the graph. So first we'll divide both sides by 2. Then we'll perform the natural logarithm of both sides. Pull t out the front. And then divide both sides by ln 1.16. Okay, so it doesn't make sense to leave the answer like that, does it? So in the context of the problem, ln 50 divided by ln 1.16, 26 months. 26.35, 26.4 months. Okay, and so that's an answer you can get from graphing this equation. Alright, let's recap how we would graph it. Follow along here, because remember, V window is important. So let's go into the graph. And we're going to type in y equals 2 times 1.16 to the power of t. And then we'll press Shift F3 to bring up V window. X min, X max, Y min, Y max. Alright, so in order to set the constraints for the V window, we have a population of rabbits, right? So the population is on the y-axis and we have time on the x-axis. Now I've said we only consider positive values of time, so our x min is 0. As far as the population goes, the population can't go below 0, so we're going to set our y min as 0 as well. Now we're interested when the population reaches 100, so maybe we'll put in here for our y max 120, and then for our x max, well, we saw here after 26 months it reaches 100, so maybe we'll put in here 30. Now this one can be a bit of guesswork if you haven't performed the calculation before, but just start with 10. If you can't see it, you double it. If you can't see it, you double it, and you just keep making that x max bigger and bigger. And that's going to give you a nice graph that looks something like this for you to copy. Okay, maybe, how about that? Say again? Oh yeah, we're going to go right now?
In the next couple.
In the next couple. Yep, cool. I'll make sure they're ready. Yep. Excellent. All right. Yep. All right. We're going to wrap things up, guys. So hopefully that skill makes a bit of sense today.
Can I just grab a couple chairs?
Yeah, that's fine. Yeah, that's fine.